All right. If anybody looks at this and notices it's really blurry all of a sudden, let me know and I'll try to
Can I
fix
be
it.
your cameraman, like turn it back and forth for you?
I don't know if you need to do that.
Alright.
If you want to, but you can just leave it there. What are you doing, Nick?
What?
Do you know how intentional that was?
Can I use your snake?
No.
No.
Okay. So,
I didn't see anything in the comments.
see anything in what?
The comments, like,
I haven't actually looked at it yet. It caught me off guard. I'll give you credit for it. I didn't really grade everybody else's. I was just checking to see if it was done. So you grade your own. This is for your benefit, not for. If you miss all of these and that teaches you how to get that out of your system and get them right the next time, that's great. I don't care that you missed all these, as long as you get them right on the test. So number 1, 16 atoms. Atoms are the circles. Atoms are circles.
I don't like your attitude.
That's a really bad overgeneralization to say atoms are circles, but for this test it'll work. Atoms are, although this looks like an atom in an atom, but don't get confused by that. Number 2, how many elements are there? There are 8. I just went through. I made myself a little list. I found this is the best way for me to not skip anything. I start from the left. Whenever I see a different element, I write it down. So there's argon, oxygen, hydrogen, carbon, helium, potassium, bromine, and nitrogen. 8 elements in there. How many ions? 4. So this is a negative ion, positive ion, positive ion. This is not one ion. It's an ionic compound or a little clump of potassium bromide. I think it's potassium bromide. And but it's got 4 ions in it. The molecules are things with the lines between them. And last class, does anybody care why this has 3 and this has 2? Anybody want to know? All right, well, you can find out in chemistry. Last class, they want to know. There's a reason, but you don't need to know. Do you want to know, Tigran? What's that? What?
Yeah, sure.
Yes, okay. So the reason has to do with, again, I'm not a chemistry teacher, so I may mess this up a little bit. Last class, I couldn't find a nice, simple periodic table like what I was hoping to find. Maybe this one will be better. So, yeah, this one really doesn't do it for me either, but it kind of does. So, this column, these have 1 electron in their outer shell. So if you were, think of these atoms as an onion, just in the outer layer, there's 1 little negative orbiting around these. These have 2. All these things, these are kind of confusing to me, not being a chemistry teacher. I don't really talk about them much. But going on to these have 5 electrons orbiting around the outside. These have 6, these have 7, these have 8. No, these have 4. Sorry.
Oh.
Come on.
Well, let me work backward. No, these have 3. Let me start over. So these have 1, 2, 3, 4, 5, 6, 7, and 8. And what all the atoms want is they want to have 8 electrons in their outer shells. So these are all happy. They don't ever get together. You won't ever see AR2 or NE2 where there are 2 of them hooked together. But you do see O2 and you do see N2. And the reason you see those is because that allows them to get their needs met. And here's how they do it. So nitrogen is in this column 5, which means 1 nitrogen atom. It's got, I think, a couple of electrons in this shell. But the important thing, let me just get rid of that. In its outer shell, it has 1, 2, 3, 4, 5 electrons. And it's not happy because it wants to have 3 more. And if it gets together with another nitrogen that has 5 electrons, they can do this sharing thing so that they then both have 8. So what they do is they come together and they share like like this. So this nitrogen is contributing 5 electrons, and this one's contributing 5, but they're sharing these 6 that are in the middle. And each pair of electrons that are being shared is represented as one of the lines in my diagram. So I'll draw nitrogen as looking like this, with what's called a triple bond, because it's sharing 3 pairs of electrons. That gives this one access to 8 electrons, and this one has access to 8 electrons, so they're happy. Oxygen's a little different. Oxygen does this. Again, I may not be doing this exactly right. Ask the chemistry teacher if you want to know. So each oxygen has access to 8 electrons, and to do that, they have to share 2 different pairs. So oxygen is shown with a double bond. That's what's going on in those pictures. Any of those pictures where you have 2 lines, that's 2 pairs of electrons. 3 lines is 3 pairs of electrons. And you don't have to remember any of this until chemistry, and they'll teach it to you again. So that's what that is. And this is not, no electrons are being shared at all. They're keeping them to themselves. They're just pulled together by the charges. So,
2 negatives are pulled together.
oh yeah, that's bad. I shouldn't have that. These should be pushed out a little bit so they're not touching. Good point. I made up the diagram and I screwed up. Thank you, Nick. So the molecules are all the ones with the lines, and the lines just mean pairs of electrons that are shared. Compounds are, this is a compound, that's a compound, that's a compound. The reason they're compounds is because they have different types of elements together, bonded somehow. It could be like this sharing of electrons is called covalent bonds, or it could be like that, that's called an ionic bond. It doesn't matter, it's still a compound. For number, whatever this one was called on your sheet, because I messed it up, it's A and E. These are the ones that are not compounds and they're not molecules, they're just atoms.
Or elements.
Yeah, they could be elements, yeah. So if you said elements, great. But I think atoms is better. For this one, the top 3, which ones are one of the top 3 things found in air? There's argon, that's number 3, it's about 1% of air. And there's nitrogen, that's 78% of air. The atomic weight of item E, so this, you just look down here and look at that number and round to the nearest whole number. The reason that's not a whole number is because if you take 1 billion helium atoms and you find the weight of each one, sometimes you're going to get a heavier one. And most of the time you'll get a lighter one. And when you average all those together, you get a number that's not exactly 4. We'll talk about why that is later on in the year. They're what's called isotopes. They have different numbers of neutrons. But you don't need to know that. That's just why the numbers are weird, because it's an average. So, Senna?
6. Why is there 2?
Because none of this other stuff is really common in air. There's water in air, but it's not the most common things. Just jumping down to, I guess this is on the next page. You're supposed to list the most common substances in air. So number 5, nitrogen is the big one, and then oxygen is about 20% of air. Argon is a little less than 1% of air. And then next comes carbon dioxide, which is really a small part of air. Some of these other things are found in air. Anybody, can you recognize, other than water, something else is found in air?
Oxygen.
This isn't really oxygen. It's oxygen, but it's not the oxygen we breathe. That'd be bad oxygen to breathe. But it's good. We need it in the atmosphere. Nick, do you know what it is? The argon? Well, the argon was listed there.
Oh.
It is.
When you write for after A, G,
A and G,
why G?
because that's nitrogen. That's most of air. N2.
And how come, oh, never mind.
So this is ozone, and ozone does a good thing in our atmosphere. We couldn't breathe and survive. There's the ozone layer filters out harmful rays, and carbon monoxide. There's probably some of that given off by people's car exhausts and other sources. Helium. There's helium just floating around in the atmosphere too. I doubt there's a whole lot of this floating around in the air. It's probably just solid. All right, the molecular weight of item D, you just find the atomic weight of carbon and the atomic weight of oxygen and add them together. Carbon is 12, oxygen 16, so together they're about 28. If you're in biology, you probably recognize this. This is glucose, C6H12O6. If you didn't get exactly 12 on the H, it might have been confusing. This is a strange way to represent this. H2 is 2 H's here. Just add up all the H's and it comes out to 12. There's 6 O's, 6 C's. And if you put it in a different order, it's okay. Again, Mr. Hirschman's method of going from left to right is wrong here. Carbon is farther over to the right, and then we go back over for hydrogen and back for oxygen. Solid, liquid, and gas. 14 is liquid, 15 is gas, 16 is solid. I don't think I need to go over those. Number 17, I put an asterisk here because I really think there is another answer in this specific situation that would have been okay. The kinetic energy of a molecule is calculated with 1/2 mv squared. That's the straightforward answer. That's probably what you guessed. But if you just have a molecule in a box, and this molecule is bouncing around, point over to that. This molecule is bouncing around, and you did 1/2 mv squared. That would give you the kinetic energy of that molecule and what else?
Temperature.
The temperature. Because the temperature is the average kinetic energy of all the particles in a substance. If you just have one particle, then the average is its kinetic energy. So in that specific situation, it'd be okay to write the temperature. And heat is transfer of energy. Temperature tells us average kinetic energy. Absolute zero is when all motion stops. That was never in your notes, but it's an easy one to comprehend. Thermal energy is the sum of the kinetic energies of everything.
Why did you do 19.5?
I don't know, because I didn't want to renumber things and I wanted to stick something in there. But I think on yours it's changed, right?
Yeah.
So yours has different messed up numbering. It's got a new whole messed up numbering format than last year. This is from last year. I changed a few things on here. I tried to fix everything, but it didn't. So 21, 22, and 23 are radiation, conduction, and convection. Radiation is just what's hitting this board right now. Even if we were out in space, you'd be able to do this. We could project images using light. Conduction, you've got to touch something. The board's giving me energy through conduction right now. Actually, no, I'm giving the board energy. It feels cool, so that means it's taking my heat away. And convection would be if I go, I just sent a little blob of warm air over in there, and that took some heat with it. The wholesale movement means you take a whole mass of something that's warm and move it along instead of just touching warm things to cold things, or instead of projecting energy through space using radiation. Number 1 down here, you could give a lot of different examples, but I gave the example of a swimming pool. This is an example of something that's colder, but has more thermal energy. So a swimming pool at 293 degree Kelvin, I don't care if you really gave me a specific temperature. Compared to hot coffee at 360 degrees Kelvin, the swimming pool has more thermal energy because even though the molecules in the water in the swimming pool are slower than the hot coffee, there are many more of them. So the total thermal energy is more than the energy of the hot coffee molecules. If you compared a cup of hot coffee to a glacier, which would have more thermal energy? A glacier. And it's not at absolute zero, which means its molecules are moving around, and it's so big that even if you have a super hot cup of hot coffee, it's still going to have less thermal energy than a glacier. What's happening to an object that's gaining heat of vaporization? It's evaporating, or you could say liquid is turning to gas. Losing heat of vaporization, it's condensing, or you could say it's going from gas to a liquid. The next couple about heat of fusion. Heat of fusion and heat of vaporization are really the same thing. We're just talking about different states of matter. So heat of fusion, if you're gaining it, you're melting it. You're going from a solid to a liquid. If you're losing it, you're freezing. You're going from a liquid to a solid. And last class, everybody just kind of sat there and looked at me, and sometimes they would nod. And then when I was all done, they would say, I don't get any of this. So if you don't get any of this, will you stop me when you don't get the first thing, and then we'll take care of it. Number 4, what's happened to the temperature of a substance that's gaining heat of vaporization, or sorry, latent heat of vaporization. I don't know if your sheet says, does your sheet say latent? No? Poop. Well, I wish I had put in the word latent just to emphasize. When something is gaining latent heat of vaporization, or you can call it heat of vaporization, but latent is good because it means hidden, the temperature is not changing. All that's happening when you give something heat of vaporization is that it's turning from a liquid to a gas. So this part, I'm happy with my answer there. The second part, I went in and talked about bonds, but I wish what I had said in the second part was temperature's not changing. All that's happening is the heat is turning it into a gas. This is just my fancy schmancy way of describing something turning into a gas. The bonds are breaking, and that's allowing it to change phase. The balloon, so if you have a sealed balloon full of air and you've tied off the balloon, the first question was pretty much what's it going to have in it? And the substances that it'll have in it in order of prevalence, it'll have nitrogen, oxygen, argon, and some carbon dioxide. Mostly nitrogen and oxygen. Very little argon, very, very little carbon dioxide, but a lot of other stuff in small amounts. As you heat up the balloon, what happens to its volume? Now, you'll notice the way I stated this is different from the way it is on yours. And here I say, in your explanation, you must demonstrate an understanding of volume. On yours, I think I said you have to define volume, because last year people were just ignoring that part. So the volume increases, heating causes the molecules to speed up, so they push against the balloon's walls, causing it to expand outward. Draw what's happening here. But this is the balloon before you heat it up, and there are little particles in here, atoms and molecules flying all around. When you heat it up, they're going to fly faster. So when they hit the walls, they're going to push the walls out. That's what makes the balloon expand. The balloon gets bigger, it moves out like that. And somewhere in your answer, you have to communicate that volume is size. Size gets bigger. I think maybe what makes these questions hard for people is that we're putting together everything you've done all year, just combining all the information. Number 7, what happens to the mass? Mass is stuff. Matter is stuff. Mass is the amount of stuff in an object. So the amount of stuff's not going to change because it was sealed. Number 8, this is what's happened to the density of the thing. And density decreases, becomes less dense. If the balloon's mass is unchanged, meaning the stuff in it's unchanged, and the volume increases, then the inside's going to be less crowded. Let me make my drawings right. So I've got the same number of particles in each one. So if we have 4 particles in here, and the same 4 particles in here, they're going to have more space, it's going to be less crowded, this is less dense. There are a lot of different definitions for density other than crowdedness, but that works here. This is going to be more likely to float, this will be more likely to sink. Some people have a hard time with this because they think of the balloon getting tighter and harder, and they think harder means more dense. It doesn't. It doesn't mean that. There's just more pressure in it because those few molecules are pushing harder than they were before. Number 9, this is the bottle thing. If you screw a lid on and you squeeze, what happens? Temperature goes up. Why does it happen? It's because when you squeeze, you push the molecules and that speeds them up. Any questions about this stuff so far? So your job now, take the next 20 minutes and do the rest of it. B1-2, they had a really hard time with this. They got really frustrated, and that's why at the end I think they voted to have the test next Thursday. But I think there are 2 questions on here that require leaps of intuition, and I'll give you a hint on those right now. They're number 15 and number 16. Number 15 and 16. 15 asks you, why are many of the rainforests of the earth located at the equator? 16 asks, why are the poles deserts? And the hint I want to give you there is, one of these you have rising air, and the other one you have sinking air. And the reason you'll have rising air at one and sinking air at the other is because the temperatures are different in these locations. If you have air of one temperature, it's going to rise. If you have air of a different temperature, it's going to sink. So knowing that, you can apply what you learned in 14, or what you went through in 14 to 15 and 16. 14 is asking about when air rises, you get clouds. When air sinks, you get clear skies. Explain why. That's a hard one. But once you buy into the whole rising air is cloudy, sinking air is dry part, you'll be able to get 15 and 16. Cameron?
For number 9,
Yeah.
you're just saying like squeeze and just push the molecule speed up. Is that basically just saying is like they're being compressed rapidly?
Yes. Yeah. Well, I'll make another cloud in the bottle when we go over these again. But this is just when I do that, I'm compressing it, and part of what compression is the walls going in and hitting the molecules. And then when I release, I'm not really doing anything, but what I'm letting them do, they're pushing my hands out. My hands really want to be here. In order to make my hands go closer together, I have to push. And I don't have to pull my hands back because the air inside does it for me. It's like a spring in here. I can push the spring, or the spring can push me. And when I push the spring, who's gaining energy? Me or the spring? The spring. When the spring pushes me, who's gaining energy? Me. And who loses it? The spring. So air is like the spring. You can put energy into it, or you can allow it to put energy into you. So do these, work together. If you need to, ask me for help if you need to. Don't. There's no shame. You shouldn't feel any worse than last block. They had a hard